Welcome back, pirates, and again, random internet people here. We are going to look at our second topic on nuclear balancing, which is on fission and fusion. I promise it's going to take a lot less time than the last one because we've actually already learned all of the basics of all of this. In our previous video, we looked at alpha, beta, and gamma decay. These are naturally occurring radioactive processes. In this one, we're going to be looking at a couple of man-made processes called fission and fusion. Fission is a man-made nuclear process where you take a big nucleus, a big unstable nucleus, smack it with a neutron. That's going to make it even more unstable. And that big nucleus then splits into a couple of daughter nuclei and usually a few more neutrons that will continue a chain reaction. So this picture here kind of walks us through that. What we've got here is we've got a big unstable nucleus like uranium-235. And we're going to smack it here with one of these guys, which is a neutron. So please be aware in a neutron that you've got a mass of 1 and an atomic number of 0 there. That's the case for all neutrons. That's going to be important for us later. So you smack it with a neutron, and then what happens is it grows into an unstable nucleus, even more unstable. And then the nuclear strong force is not enough to keep that guy together, and so it breaks into some smaller daughter nuclei. In this particular case, it looks like a nucleus of krypton and a nucleus of barium, but that's going to be random and different every time you do it. And it also gives off a whole bunch of energy that you're going to be needing for whatever application that you'd like to have for this. And you're also going to get 3 more other neutrons that are over here that are going to be important because they're going to continue what's called a chain reaction. So what happens in a chain reaction is, if we look at this beyond an individual reaction, you've got one unstable nucleus being hit with a neutron here. So that's what we showed before. And again, that breaks into this and this as just examples. And then again, there's those 3 other neutrons that we talked about. But each of those 3 other neutrons can then go and smack another atom of the uranium, which is then going to break into a couple of random daughter nuclei. Please note that these 2 here that I'll put in purple are different daughter nuclei than what we had over here in orange, because every time we do it, it's just kind of random. And then that's going to give off a few more neutrons that are going to go, and they're going to continue the process into another one over here that's going to break into something else, again, a little bit different than before. And so, again, this is called a chain reaction because you start it with 1 that I've got there in the orange, and then it continues at a whole bunch of different levels, so you get a whole bunch of these things going at the same time. Now, if you control this process, then you have what's called a nuclear power plant. You can moderate the amount of neutrons that are being released and the amount of energy that is being put forward, and you can run a power plant that way if you control it. If you don't control it or don't want to control it, then you have what's called an atomic bomb. So you get that chain reaction starting, and then within a fraction of a second, you have more energy than the system can contain, and the thing explodes. And explodes with quite a force here. The ones that we dropped over Hiroshima and Nagasaki were in the payload range of about 15 to 20 kilotons, which does not mean that the bomb weighed 15 or 20,000 tons. That would be ridiculous. What it means is that if you piled up 20,000 tons of TNT and lit the fuse and ran away, that's what would go off. So again, I'm going to say that out loud, 20,000 tons of TNT. So one bomb explodes with the same force as 20,000 tons of TNT. So obviously we're talking about a great deal of energy when you're starting to hear talk about the idea of energy. Now, you could spend a lifetime studying processes such as this, but we're just going to get into the whole balancing aspect of things. And so the same rules that we looked at before apply here. It's just going to look a little bit different because of the presence of these neutrons. And the basic idea that we saw before was that anything that occurs on the left-hand side of the equation over here has to end up being the same as everything over here on the right side of the equation as far as numbers are concerned. The elements can change because these are nuclear reactions. This does not normally take place in a chemical reaction, but these are nuclear reactions. You just have to make sure that the numbers on the left are the same as the numbers on the right, and that goes for the top numbers as well as the bottom numbers. So let's start over here. Let's split this in half. There's our left and right. And you'll notice that in this case, I've got a 1 and a 235. So if I add up a 1 and a 235, obviously that is 236 between those two that are there. If I then compare that to the numbers that are over here, 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 and here, I should also get 236. Well, let's check it out. 141 and 92, that's 233. And then one more over here for this guy is 234, but that doesn't match. Except that it does, because remember, there's not just one neutron, there's 3 neutrons. So this 3 that's in front here tells you that there's really 3 of the ones that are there. So really, that's a 3 plus 92 plus the 141, and add all that up, and you get your 236. Now, if you don't like that, if that's going to cause problems for you, then what I suggest that you do is you scratch out the 3, and you write the neutron 3 times. So 10N and another 10N, so you've now written it 3 times. And now I've got 141 and 92 and 1 and 1 and 1 that's there, and all of that adds up to be the 236 that I had over here. So the 236 on the left top is the same as the 236 on the right top. Now if we look at the bottom numbers, I've got a 0 and a 92, so clearly the two of those guys together gives you 92. And then I just have to make sure the numbers on the bottom add up. That's 56 and 36 and a whole bunch of zeros. But 56 and 36 is also 92. So again, those things match. That's there. So all you have to do is make sure that the numbers on the top left match the numbers on the top right, and the numbers on the bottom left match the numbers on the bottom right. So let's take a look at this. It says, fill in the missing nuclear piece in each of the following equations. So these 3 samples look exactly like this up here, except that you'll notice that the bottom numbers are missing from everything for a couple of reasons, not the least of which is it's a total pain to try to type them out on a word processor, let alone in the olden days like using a typewriter. But you really technically don't need them as long as you have a periodic table. So a couple of things to remember, that all of the neutrons are zeros. So anything with a neutron is a 0 at the bottom here. So I'm just going to go ahead and fill in a whole bunch of zeros because neutrons don't have any protons. That's why they're zeros. And then all I need is access to a periodic table, and if I have a periodic table, then I can figure out the bottom numbers. So I can look them up. Uranium is a 92 that's there. So here we go. Uranium is a 92. And apparently I've got barium there. And so here is barium. Barium is a 56. So I'm going to go ahead and put in a 56 that's there. So what is here if I started with these things over here and ended with these things over here? And remember that all the numbers in the top left have to equal all the numbers in the top right. And all the numbers in the bottom left have to equal all the numbers on the bottom right. So obviously I've got 1 and 236 just like I did before. 1 and 235, that gets me 236, I should say. So then I've got 144 and then a question number. I don't know what that is going to be. That's what I'm going to have to figure out. And then I've got here, again, a 1 for each of these neutrons, but don't forget that there's 2 of them that's there. So really that's a 2, or if you prefer to write the neutrons twice so that you don't forget, then that's fine as well. So I've got 144 and 1 and 1. And then I've got 236 over on the other side. So 236 minus 144 and another 1 and 1 is going to get me 90. So I am missing 90 from up top. 144, 90, and then 1 and 1. Gets me the 236 that I'm missing. Now, as far as the bottom is concerned, once again, I've got 0 and 92 down here, so that means I've got a 92 in totality. And I just have to make sure that all of my numbers down here add up to be a total of 92. I've got 56 and then an unknown number here and then a bunch of zeros. So really all I got to do is take 92 minus 56 and I get 36 out of it. So that number down there is 36. So what element is that? I don't know. Let's look it up. So I go back to the periodic table here and I find element 36. There it is. It is element Kr, krypton. So then that is the element krypton that is there. So that's all you do. All you do is, just like we did in the other examples, you make sure that the numbers in the top left are the same as the numbers in the top right. The numbers in the bottom left are the same as the numbers in the bottom right. And you find the bottom numbers by comparing their symbols on the periodic table, or find their symbols by taking the number in the bottom and looking it up in the periodic table. Let's look at a couple of examples, a couple more examples of this fission thing. Another fissionable material that you can use is plutonium-239. So if I add up 1 and 239, clearly I'm going to get 240 that's there. So 240 is my total on the left, and that means the total then on the right has to also be 240. So that's going to be 134 and 3 groups of 1. And again, if you can't remember to do that, then you got to remember to write this 3 times so that you don't forget to include it thusly. So that is 240, and we're going to subtract the 134, and we're going to subtract 1 3 times. So that's going to leave you with a 103 up there at the top, 103. Now, as far as the bottom numbers are concerned, going to have to look those guys up. Going to have to look up xenon and plutonium. So let's see, xenon is down here at a 54, and plutonium is down here at a 94. Yes, plutonium is a 94 there. So the plutonium is here at a 94, and then this was 54. So I've got 54 and some other number that I'm not sure of and a whole bunch of zeros. So it's really just 94 minus 54 gets me 40. So my number down below here is the number 40, which means that I can go back to my periodic table and find element number 40. There it is, zirconium, like so. So this is ZR. That is there. Okay, let's see. Our last one here is another one of these plutonium-239s. So the 1 and the 239, again, go together to make a 240 up top. Everything on the right then has to equal 240. I've got a 111, and then 4 groups of 1, so really that's 115. So that's 240 minus 115 gets me 125. So my top number is 125. And then my bottom number down here is whatever plutonium is and whatever palladium is. Now, plutonium is a 94. We had just looked that up in the previous problem here, so that's going to be the same. But I can look up palladium on the periodic table here. So once again, here is plutonium there at 94, and palladium is here at 46. So palladium is going to be a 46. And again, I got a whole bunch of zeros over there. So that's 94 minus 46 gets me 48. And now I go back and figure out what 48 is, and that looks like it's cadmium on the periodic table. So that one there is CD. So fission is the process of taking a large atom, using a neutron and smacking it into smaller daughter atoms and more neutrons to continue a chain reaction for a variety of different purposes. Fusion is the exact opposite of fission. In fission, we're taking something big and breaking it into something small. In fusion, we are taking a bunch of small things and smushing them together to make something big. This is the process that occurs on the sun. So we're talking about huge, gargantuan, insane amounts of energy that are here. So normally you're talking about something like isotopes of hydrogen that are going together to make something like helium. Which again is what takes place on the sun that's there. Now, if you can control this process, then you've got what's called a fusion reactor. The problem is that right now it takes so much energy and pressure to get the fusion reaction started and so much energy to safely contain the fusion process that we have no working fusion reactors on the planet right now. Now, that's not quite true. We have fusion reactors that work, but right now it takes so much energy to get it started and safely contain it that we don't actually make any energy on the backside out of it. So in other words, it takes more energy to do the process than we get out of it, so it's not efficient. If we're not worried about controlling it, then you're talking about what's called a hydrogen bomb. And if you thought that an atomic bomb was bad up here, where in Hiroshima and Nagasaki, that would be like lining up and dropping 20,000 tons of TNT on a target. Hydrogen bombs are even worse because a hydrogen bomb has a payload of about 9 or so megatons, which means that's like dropping 9 million tons of TNT on a target. So again, think of the pile of a ton of TNT. Now do that 9 million times. Now set that all off at once. That's what a hydrogen bomb is. So you are talking about, again, just an unfathomable amount of energy, which is why it's so difficult to contain. So again, right now, we spend more energy trying to safely contain a fusion reaction than we get out of it. This is one of the holy grails of your generation. If you could figure out how to safely contain a fusion reaction here on Earth, then we would never run out of energy ever in the history of our species, because this basically runs on hydrogen, which we have a virtually limitless supply of. So if you could figure out how to run safely a fusion reaction system, we will never run out of energy ever. So put that on one of your life goals and see if you can figure out how to do that. Now, as far as what we're going to be expecting you to do for these reactions, it's the same thing as before. It's just that the reactions are going to look a little bit different. All you got to do is make sure that the numbers on the top left are the same as the numbers on the top right, and the numbers on the bottom left are the same as the numbers on the bottom right. So up here, I've got two different isotopes of hydrogen, one called deuterium and one called tritium. One's a 21H and one's a 31H. You put those together. Don't even need a calculator for that one. I can do that with one hand fingers. So that's a 5. And then over here, I got a 4 and a 1 that go together to make a 5. The 5 equals the 5, and you're in good shape. Down below, you just got to make sure that your bottom numbers are the same as well. 2 and a 1 is 2, and 2 and a 0 is 2. So that's all we're doing. We're just making sure that the top numbers on the left equal the top numbers on the right. The bottom numbers on the left equal the bottom numbers on the right. And remember, of course, that neutrons are zeros here. So already looking ahead, I've got 0 and 0 for neutrons. Neutrons have no bottom number. Now, the nice thing is there's a whole lot of hydrogen and helium involved in this. So when we start to look at hydrogen and helium on the periodic table here, hydrogen is number 1 and helium is number 2. So that's nice. Don't even have to look those up anymore. So hydrogen here is number 1 and number 1. So let's take a look at what happens up top here. Up top here, I've got 2 and 2, and then I've got 1 over here. So again, all I need to do is put a 3 there so that the 3 and the 1 go together with the 2 and the 2 so that the top numbers match at 4. And again, it doesn't matter what the number is as long as they match. And down here, I've got 1 and 1, and then something and 0. So obviously, that's going to be number 2. And without even looking it up, although I will, number 2, again, is helium here. So that would be an atom of helium that's there. So what happens here? Well, let's see. I got a hydrogen there, so that's a number 1, and I got a helium there, that's a number 2. So what's missing here in that one? Well, up top, I've got a 2 and then some other number, and then up top here I've got a 4 and a 1, so that's 5. So really the number I'm missing is 3. Down below here, I've got 1 and some other number that's going to go together with 2 and 0. So obviously I'm going to have 2 over here when those guys go together. So this also has to be 2, so this has to be a 1. So this is a different isotope of hydrogen that's there because it's number 1. And then in our last one here, I've got 1 hydrogen with something, so that's a hydrogen, so that's a 1 down here. And I'm going to go with something here. And the only thing that's different about this one, notice, is it's 2 heliums. So what we're really saying is that it's 2 4-2s, or again, if you don't like that system, then go ahead and draw it twice. So it's 4-2-He and 4-2-He that's there. So what you've got up top here is you've got 4 and 4 that's going to go together to make an 8. So that means whatever numbers these are together also have to make an 8, which means that I am missing a number 7 up top here. So this one here has to be a 7 so that the 1 and the 7 go together to make the 8. And then down below here, I have got a 2 and a 2. So that's obviously a 4 that is there. And so whatever happens here and here also then has to be a 4. So the number I am clearly missing there is a number 3, so that the 1 and the 3 go together to make a 4. And then all I got to do is look up to figure out what element number 3 is, and number 3 is an atom of lithium. So that is lithium there. So fusion is a far more energetic process that only occurs naturally in places like stars and the sun. We do have man-made here on Earth, but right now we spend more energy trying to safely contain it than we get out of it, unless we don't care about it, in which case we're talking about the most devastating weapon mankind has ever created, called the hydrogen bomb. So fusion is taking something small and putting it to something large to create energy, and fission is taking something large and breaking it down to something smaller to get energy, both of which are easily balanced using the same processes as we talked about before.